Here we'll discuss CT collapse pressure calculation. This lecture is in continuation with our previous lecture entitled CT burst and collapse limits. So we'll just recap the main headings of the previous lecture, that is part 1. So in part 1 we discussed introduction to CT operating limits, definition of burst and collapse pressure, formula used for calculation of CT burst pressure. And now here in this video we will discuss formula used for calculation of CT collapse pressure. So talking about the collapse resistance calculation or collapse pressure calculation, we will discuss two approaches. The first approach is radical approach. It is also known as plastic hinge model, and it is valid only for OD to wall thickness ratio less than 14. According to radical approach, collapse pressure P sub C is equal to P sub CO into KY. Now let's see what is P sub CO and K sub Y. P sub CO, whose formula is given over here, is collapse pressure without considering the tension effects or without considering the axial forces effect. So P sub CO is equal to sigma sub Y into T over OD into 2 square root 1 plus OD over T into 1 minus phi over 4 into phi over 2 and the square of this particular term minus phi into OD over T into 1 minus phi over 4. Here sigma Y is the minimum yield strength in PSI, T is wall thickness in inches, OD is outer diameter in inches, and phi is tubing ovality in fraction. The second factor of the formula K sub Y is written over here. K sub Y is the factor which is used to incorporate the effect of axial forces or tension in the CT string. So K sub Y is equal to square root 1 minus 0.75 into F axial over sigma Y into A sub wall plus Pi over sigma Y whole square minus 0.5 F axial over sigma Y into cross sectional area plus Pi over sigma Y plus 2m over into Pi over sigma Y. F axial is axial tension in pound force, and A sub wall is cross sectional area in square inches, and m is basically a constant which we can calculate using this formula OD over T square over 4 into OD over T minus 1, and Pi is the internal pressure. The second formula or second method we will discuss is the conservative approach known as Timoshenko model, and it is valid for any ratio of OD to wall thickness. According to this conservative approach, collapse pressure is equal to P sub Y into P sub E into 1 plus 3 phi OD over T minus square root Py plus Pe into 1 plus 3 phi OD over 2T square of this particular term minus 4 Py into Pe over 2. Here P sub Y is yield collapse term which is used to account for the tendency of tubing to collapse due to the weakness of the material. We can calculate this P sub Y with this particular formula. P sub Y is equal to gamma sigma Y into 2T over OD. Here gamma is the axial stress correction factor which is used to account for the reduction in collapse pressure due to axial stress, and we can calculate gamma with this formula. Gamma is equal to 1 minus 3 sigma axial over 2 sigma Y whole square minus sigma axial over 2 sigma Y. P sub E, which is in our original formula, is stability collapse term which is used to account for the tendency of the tubing to collapse due to imperfections in its geometry. Formula for P sub E is equal to 2E over 1 minus mu square into T over OD whole cube. Here are the terms which are used in this all these formulas. sigma y is the minimum yield strength in psi, T is wall thickness in inches, OD is outer diameter of the coiled tubing string in inches, phi is the tubing ovality in fraction, sigma axial the axial tension factor, E is equal to modulus of elasticity, and mu is the Poisson's ratio for the steel which is being used for coiled tubing string. Now to understand both of these models or both of these formulas which we have discussed, a radical approach and the conservative approach, will solve some examples with the help of this spreadsheet. So here in this sheet we have incorporated the above mentioned formulae. Now let's see how the collapse pressure is affected with the different parameters. So for example, we are using 1.5 inch coiled tubing string with 0.134 wall thickness, material yield strength is 80,000, ovality is 1%, and axial force is, let's say, 0, there is no axial force, and Young's modulus for the steel is 28 into 10 to the power 6, and the Poisson ratio for the steel is 0.33. We can see the result over here. Collapse pressure according to the radical approach is 13,518, and collapse pressure according to the conservative approach is 11,650. Now we'll see the effect on these collapse pressure values by changing different parameters one by one. So if we just increase the wall thickness from OD of the coiled tubing string from 1.5 to 1.75, we can see the when we are increasing the OD keeping all the other parameters same, collapse pressure is going to decrease. Okay, these values are going to decrease. Okay, now if we change the wall thickness from 0.134 to 0.156, collapse pressure value is increasing. Okay, so if other parameters are constant and with the increase in wall thickness, collapse pressure will automatically increase. Same applies for the yield strength. If we use a yield strength of, let's say, 90,000, our collapse pressure has also increased from 14,000 to 15,000 approximately, and also for the radical approach. Here the key parameter needed to note is the ovality. Just see, if we have 0% ovality, we have 18,720 collapse pressure for these parameters. But if we just put 1% ovality, okay, so collapse pressure has reduced significantly. If we go 0.02% ovality, collapse pressure is reduced further. 0.03, collapse pressure is reduced significantly. 0.04, 0.05. See, so with the increase in ovality, there is a huge decrease in collapse pressure for the CT string. Okay, same for the axial tension. Let's say we have 10,000 axial tension. So here we have, before 10 axial tension, we have 10,000 collapse pressure. But if the string is undergoing a 10,000 pounds of tension, then we can see there is approximately 500 drop in collapse pressure. So the main factor for which are affecting the collapse pressure are coiled tubing OD, wall thickness, material yield strength, and ovality. Definitely axial force also affect, but it does not have so much impact as the ovality. So that was the discussion about collapse pressure estimation. Thank you very much for watching. See you in the next lecture.